Hydrolysis and condensation reactions are also a very common type of reaction that you would see. They are characterized by, in this case of hydrolysis, cutting with water, hydrolysis. So we cut with water, we add water to a compound. You can see here we're adding OH and H. So we add H2O. OH goes to one side, H goes to the other side. We're adding water, so we cut with water, hydrolysis. Let's do another activity, though, and start preparing for biochem. My question to you is, what kind of molecule is this? In terms of, this is a biological molecule, I'll give you that hint. Is this a carbohydrate? Is this a polypeptide or protein? Is this a lipid, fatty acid chain, some sort of lipid? Okay. What kind of molecule is this? The answer is this is a polypeptide. I know because I have this peptide, this amide bond. This molecule has a lot of nitrogen in it, and nitrogen is only found biologically on nucleic acids in terms of macromolecules, biological macromolecules, on nucleic acids and on proteins. This is not a nucleic acid, right? This is not DNA or RNA or ATP. It has this amide bond or a peptide bond, so this is a polypeptide. Next question is, how many amino acids are there on this polypeptide? So let's count together. I've got 1 amino acid, 2 amino acids, 3 amino acids, 4, 5, and 6. I have 6 amino acids here. The AAMC has not publicly indicated whether or not you need to memorize the names and the structures of all of the amino acids. We're going to talk about the amino acids, and you will definitely need to know the different categories, the types of amino acids. So polar, nonpolar, positively charged, negatively charged. And it couldn't hurt to know some examples of each type of amino acid. There's 20 different ones. In an introductory biochemistry course, you probably talked about the structure of the different amino acids. So for situations like this, it's probably better to just err on the side of caution and know the structures. But it is entirely likely that you'll be able to get away without knowing the individual structures and be able to recognize them. To the extent that you do or would need to memorize them, you will not need to be able to recreate the entire structure. So for example, if I tell you that a protein has the amino acid valine, you wouldn't need to be able to reproduce its structure, but you would need to know, for example, that valine is an example of a nonpolar amino acid because it has an aliphatic chain. Okay. So that's our little preview into biochemistry. So this is our hydrolysis reaction. Condensation reaction is the reverse. So in a condensation reaction, we remove water. With a molecule, we pull out an OH from one side, we pull out an H from the other side, and we've pulled out water. We've condensed the two. This is sometimes also called a dehydration synthesis reaction. Transesterification. So this is a type of reaction where it seems like a very obscure and probably unimportant type of reaction, and specifically transesterification probably is. But the reason I have this here is because it gives us a really good example of a nucleophilic substitution that is not an SN1 or SN2. It gives a really good example of nucleophile attacking electrophile and leaving glucose null, just as a generic understanding of reaction mechanisms. So what happens is a catalyzed reaction, either acid or base catalyzed. Let's suppose it's base catalyzed. So I'll have this methanol, and in the presence of a very strong base, it'll become deprotonated. So I'll have what we call the methoxide anion or an RO group. Right? This is an alkoxide ion. It's a very good nucleophile. It's going to go and it's going to attack the electrophile. Where's the electrophile here? The electrophile is the carbonyl carbon, which is consistently going to be an electrophile. And so the leaving group comes off. This is my leaving group. And so you can see it came off and my methanol came on. Nucleophile attacks the electrophile and the leaving group comes off. Great example of that mechanism. And we're going to dive deeper into this in the next organic chemistry lecture. But again, it's important to be able to understand why these reactions are occurring, to be able to identify the nucleophile and the electrophile. In this case, understand why it needs to be catalyzed, because the methanol is not a good nucleophile, but its conjugate base is a very strong conjugate base, is a really good nucleophile. Okay. Alkylation reactions. There are no specific alkylation reaction mechanisms that you need to know. In fact, the Friedel-Crafts alkylation is not on the MCAT. So if you are using some textbooks or some websites or other resources that are referring to this mechanism, to this reaction, you do not need to know this for the exam. It's not on the syllabus. And this DNA methylation mechanism is very highly complex. It's far beyond what's drawn in this slide. All that you need to know about alkylation is to be able to recognize it when you see it. I have this benzene ring, and now I have this benzene ring plus an alkyl group. That's an alkylation reaction. Here I have no alkyl group. Now I have an alkyl group. I have a methyl group. So recognize it when you see it. Halogenation. We've got a couple different types of halogenation reactions. Addition of the hydrogen halide, free radical halogenation, and the addition of the diatomic halide. So let's talk about the hydrogen halide first, HX. Let's say I have this alkene here, and I treat it with hydrobromic acid, HBr. When the HBr dissociates, I have the hydrogen ions in solution, I have the bromide ions in solution. The double bond, remember, acts as a nucleophile. Basically, the proton comes in and attacks, takes some electrons, and forms a sigma bond. Turns a CH2 into a CH3. And what I'm left with is a carbocation, right? The carbocation is right here. Because the carbocation is a good electrophile, this nucleophile will come in, go after it, and brominate it. This is what we call Markovnikov's rule. Markovnikov's rule tells us that the halogen is going to add onto the most substituted carbon. In this case, it had theoretically had a choice. The hydrogen atom could have attacked here. It also could have attacked here. So I could have gotten this alkyl bromide, or I could have gotten this alkyl bromide. And in fact, in solution, I will get a little bit of that, but most of it will be the secondary bromide. And the reason is because the secondary carbocation is far more stable than the primary carbocation. So that's Markovnikov's rule. In free radical halogenation, we actually follow anti-Markovnikov's rule. But it's for the exact same reason. So the principle here is the same. Radicals and carbocations want to form the most stable everything. Every reaction wants to form the most stable thing it can. So in this case, we have a bromide radical coming in. And it's actually going to attack onto the terminal carbon. The reason is because when it does, it forms a secondary radical, and secondary radicals are more stable than primary radicals. If it attacked onto this carbon atom, I'd have a primary radical, and that's just not as stable. So when I have anti-Markovnikov addition, it attacks to the least substituted carbon. But again, even though one is anti-Markovnikov's rule and the other is Markovnikov's rule, the reason driving the two is the same. That is, You're trying to create the most stable intermediate and the most stable product. Finally, I have the addition of the diatomic halide, in this case, bromine. Adding it across the alkene goes through what we call a bromonium ion. We add the bromine to both sides. Notice it happens to add to the opposite sides. Now, what is a bromonium ion? Well, let's draw out this mechanism. It's a very interesting mechanism. It's fun to examine. I know this isn't the exact same alkene as was on the slide, but it's functionally going to be the exact same mechanism. First, we have bromine. And so bromine is here, and it's going to go after the pi bond, the double bond here. So the double bond will be able to donate like this. Okay. When it does that, this bond pops off, and I end up with a positively charged ion here. This is what we call the bromonium ion. So this bromine atom, now the bromide ion, is free in solution. And it's going to also want to attack onto this alkyl, onto this carbon compound. But it can't attack from here because bromine's really big. There's nowhere for it to fit. So it's actually going to come around to the other side. And these two are equivalent. It doesn't really matter for these two because they're symmetrical. But it's obviously going to attack where it's going to be most electrophilic. And it'll form a bond there. So my bromide ion comes in, forms a bond. It breaks this bond. Is no longer charged, and finishes the mechanism. This is just a single bond. Okay. You'll notice how the bromides added to the opposite sides. And so these would have opposite stereochemistry if they were chiral. Okay. So those were three mechanisms of halogenation.
For most students, and maybe you too, the CARS is the hardest section on the MCAT. It may feel like it's one of the few remaining obstacles between you and the medical school of your dreams. But as you try to prepare for the CARS, you find there is a never-ending stream of conflicting tips, strategies, and plans, none of which seem to actually help or show any results. If you feel frustrated, overwhelmed, or lost when it comes to the CARS, if you're looking for a CARS expert who has helped thousands of students achieve their MCAT CARS goals, then you found your solution. Testing Solutions MCAT CARS Bootcamp. Founded by Nick Zahner, a current medical student at Stanford with a master's degree in philosophy of religion from Harvard, Testing Solutions' approach to the CARS is revolutionary. Testing Solutions CARS Bootcamp provides day-by-day, step-by-step instruction that teaches you the techniques that produce ultra-high MCAT CARS scores. Instead of wasting your time with the needlessly complex filler that other companies try to sell you, Testing Solutions' approach to the CARS is based on the principle of minimum effective dosage. There's no wasted time, just the minimum amount of effort that is required to get you the results you want. With over 500 4.5-star reviews on Amazon, Testing Solutions CARS Bootcamp is the most trusted, proven, and effective CARS course available on the market today. You will have access to Testing Solutions' 180 meticulously designed CARS passages, the largest CARS practice library offered by any MCAT prep company in the country. Our passages are regularly rated by users on Amazon, Reddit, and SDN as the most accurate non-AAMC CARS practice passages available, consistently rated higher than Exam Crackers, the Princeton Review, Kaplan, and Next Step. Unlike some companies who prey on pre-medical student fears by charging outrageous amounts of money for their mediocre at best practice materials and courses, Testing Solutions will always charge a fair price for an amazing product. Because after all, we're not like the other test prep companies. We're aspiring doctors just like you, only a little further down the path. Let us help you do what we've already done. If you're not happy with your CARS Bootcamp for any reason, We offer a 100% money-back guarantee, no questions asked. You've got nothing to lose and the CARS score of your dreams to gain. Don't be one of the people who write us each week saying they wish they had found our MCAT CARS Bootcamp sooner. You don't have to struggle with the CARS any longer. Sign up and get started today.